Hello there. I'm going to take you through an example that uses the second derivative test. So what we're going to be doing for here is we're going to be looking at this function, um, x squared plus 4, the quantity, all to the 1/3 power, so that's the third root, minus 1. And we're going to try to find the intervals on where that function is concave up and concave down. Now that we're sort of into chapter 4 and we're looking at the second derivatives and concavity, we would know how to deal with something like this. So you might want to break out your graphing calculator and see what this looks like. And you can sort of see the function here. It's not terribly easy to see perhaps what's going on in terms of concavity. Concavity is sort of hard to figure out. It looks like it might be curling down on this interval here, and then it might be changing in curl, so curling up around this interval here, and then changing back down. But we're not really sure what those intervals are. If we have to find the exact intervals, we're not really sure what's going on there. So graphing it is a good way to see what's going on, but it's not going to tell you where those intervals are. So to tell us where these intervals are, we're going to have to use calculus. So I'm going to find the derivatives of this function. So to find the first derivative, I'm going to use the chain rule. What we're going to do is we're going to take that 1/3 power down and hold this constant, and we're going to subtract a power from the exponent, so it's going to be the negative 2/3 times the derivative of the inside. So the derivative of the inside is 2x plus 0. And then, of course, the derivative of the second point you see up here, the second term, is 0, so the derivative of any constant 0. If I clean this up a little bit, put the 2 over here and the x out in front, this is my first derivative. And here is where you actually do want to clean up the derivative first, so you can take that second derivative more easily. Now for the second derivative, you're going to have to use the product rule because you've got a product of two functions. I can't take that x into a chunk with a negative 2/3 power. And inside that, we're going to have to use the chain rule again. So something very similar to what we have here is going to show up again. So let's see how that works out here. And you see, for the product rule, I've sort of divided these functions by color. So if I take the derivative of the first, I get 2/3 times the second is just the blue part, plus I take the first just how it is, and then the derivative of the second, which should be reminiscent of this first derivative up here. So we're going to get, this time, since we have a negative 2/3 powers, we have negative 2/3 times that chunk to the negative 5/3, but taking the derivative again of what's inside, we get 2x. Now comes sort of the difficult part, because really to find concavity here, we're looking for where that second derivative is going to be 0 or undefined. So those are the two places where we could have concavity. So what that means is we're going to have to simplify this big mess, and this is where it becomes a little bit difficult. So if we look around here, we have some things in common. So we have this big chunk here in common with both terms. We have a 2/3 in common with both terms. So this would be a 4 times 2. If you work that 8 up, so I can look at that 2/3 and taking that out. So what we're going to do is we're going to take out the highest negative power here. We're going to take out negative 5/3. The reason we do that instead of taking out the negative 2/3 is because if we take out the highest negative power, then what we have left, these powers are going to be both positive, and this one's going to become easy. It's going to become to the first. So we're taking out an x squared plus 4 to the negative 5/3 and 2/3 x. So this is really what we're taking out of both of these terms up above. And when we do that, notice that the negative 5/3 plus 1, we add those powers. Negative 5/3 plus 1 would give me the original negative 2/3 that we had up here. And of course, we took out this whole term for the second one, and we're left with this 4x squared. In fact, the negative 4x squared for that second term. And we can combine these two terms together, and we get negative 3x squared. So this is our simplified second derivative. So let's see how that helps us. We want to figure out where this is equal to 0. Now notice that this whole thing here, we would have to be worried about this term here too, but it's a negative power, so we need to figure out, that flips it down in the denominator. We need to figure out where that's equal to 0, but something squared plus 4, the minimum that can be when x is 0 is 4, so we're not really worried about this term. So really, we're going to focus all of our attention on this term here in the numerator. So I set that equal to 0. I manipulate this by adding the 3x squared over, switching sides. And then I'm going to divide both sides by 3 and take plus or minus the square root. So these are my two possibilities for the inflection points where it's going to change concavity. And we sort of saw that in the graph above. So what we're going to do now, just like the first derivative test for increasing and decreasing, we're going to label these points on a number line. And we're going to check them in the second derivative. So we've broken this up into 3 intervals. We have one interval from negative infinity to negative 2/3. We have 1 or 2 over root 3. We have one interval from negative 2 over root 3 to 2 over root 3. And we have one interval from 2 over root 3 to infinity. When we plug values in for the second derivative, like maybe a negative 100 here, so these are x values. 0 is always a good one to plug in. And maybe something big like 100 here. We'll see that this is our resulting sign. Negative, positive, and negative. Notice, for instance, if I plugged in negative 100, this term we can really get rid of because that, as we said above, it's always going to be positive. So this term is always positive no matter what I plug in, because I square it and add 4, and then I take a power, so that's always going to be positive. This term is really what we need to worry about. When I plug in negative 100, I have 4 minus 3 times negative 100 squared, which is going to be some big number. So that's going to be very negative. When I plug in 0, I get 4. So that's going to be positive. And when I plug in 100, again, that 100 squared is going to be giving me 4 minus 3 times 100 squared. So that's very negative. So this tells us the concavity of the function. Essentially, from this negative 2 over root 3 to 2 over root 3, we're going to have concave up. So we're going to have the function looking something like this, concave up, curling upward. On these two outer intervals, we're going to have the function being concave down. So this is where the function is going to be curling downward on the ends. And we also know if the function changes concavity, then we're going to have inflection points. So this does go from concave down to up to down. So that tells us additionally that these 2 points here at plus 2 over root 3 and minus 2 over root 3 are going to be inflection points. So we can sort of label that on the graph above. And we can see exactly where this is increasing and decreasing. So again, this is going to be concave down until we hit the x value of negative 2 over root 3. It's going to be concave up from negative 2 over root 3 to 2 over root 3. And then it's going to be concave down again from 2 over root 3 all the way to infinity. So I hope this has helped. Thank you.